Swayam Prabha. Digital India. Educated India.
Okay. This is exactly in line with BJT as an amplifier. So we will go through similar things very quickly. Okay. So like in BJT amplifier, also here we will consider that the input signal is small, so that when we amplify it, it remains within the saturation region, okay, of the MOSFET characteristics. And we can assume that the amplifier is linear. Okay. Now, if I just, what is happening? I don't know why. If I draw a basic MOSFET amplifier where this is my supply voltage, this is the resistance which is connected to drain, and for the time being I'm just assuming that I am applying both AC and DC here, although that we know that can't be the case, but and say this is my VGSQ and this is my VGS. Okay, I don't know why the pen is not working properly today. Okay, anyway, so pen is not working. So this is VGS and this is capital VGSQ. Okay, so if I draw the IDS, I don't know what is happening, IDS versus VDS, then we will get these plots, right? And for different VGS, and we can correspondingly draw a load line, and if we assume that this is my Q point, okay, so corresponds to this is your VGS Q, and basically you are applying a signal which is changing the gate source voltage here, okay, that basically changes your IDS, right? So you will correspondingly you will get IDS here, okay, IDS will change, and also your VDS is going to change, right? And this is your VDSQ. So but we have to make sure that when the amplifier, when we apply an input signal, the amplifier output, which will move along this load line, will not go to this non-linear and cutoff region. It will remain within this saturation region, okay, for faithful amplification. So this part we know from our BJT discussion, and now if we follow the similar thought process which we used in case of BJT, um, we can have a couple of small signal components. One of the components is basically your GM, okay, and the other one is your R0. How we will get GM and R0, we will discuss that. Now for GM, we can come to GM equation, okay, from considering that uh, we have ID or IDS, that is, this contains both AC and DC signal. Remember, IDS we can write Kn VGS minus VTH whole square, okay. What is happening, I don't know, whole square. So this uh, this is in the, of course this is in the saturation region, and we can write this VGS, writing both AC and DC component, okay, and why I can't write this here, and this is basically your minus VTH whole square, and you can then write all the VGSQ minus VTH whole square, okay, that is your DC part, basically, plus 2 Kn VGS Q minus VTH multiplied by VGS, small VGS, okay, plus Kn VGS square, right? So you see, this is your DC component, and these two are basically your AC components, okay. Now we can you see this, the second term, both second and third term is time varying term, right? But we can basically here in the second term the current ID is proportional to VGS, you see, right? So what our aim will be to, if we can neglect Kn VGS square term, because that is a nonlinear term, you see, so that can give rise to higher order harmonics. So what we can do, if we assume that the second so the first term is DC, so forget about that. The second term is and third term is AC. If we assume that 2 Kn 2 Kn VGSQ minus VTH, okay, if it is much greater than VGS, small VGS, then just remove Kn, because Kn is there in both both side, okay. So if this is the case, then we can neglect the third term, okay. So we will end up with small IDS, that is the AC component of the drain source current, okay, that can be written as right, and this so we from here this is a relation between, you see, this is the output current and this is the input variation of the voltage, right? So this relation will give rise to transconductance. So transconductance means, transconductance relates output to input, okay, output to input, transconductance, but the numerator will be current and denominator will be voltage, okay. So IDS over VGS will be 2 Kn VGSQ minus VTH. Okay, so this is the expression of transconductance. Okay, this can also be defined okay, this can also be defined is equal to 2kn, is the same expression. Okay, this can be defined. You remember we have like similar definition in case of BJT also. Okay, and if we plot you can simplify, or you can have different expression of GM. You can write GM as 2 kn IDQ, okay, or IDSQ rather. Okay, I'm writing IDSQ. Okay, so 2 kn 2 root over kn IDSQ can also be written from here. You see, you just replace IDSQ is equal to, there is a square term of VGS minus VTH, VGSQ minus VTH whole square, right, in IDSQ. So that way you can replace this factor with IDSQ. Now we can plot, in fact we can plot plot IDS sorry, we can plot IDS.
Sir, can you show the previous page?
Yeah, so yeah, so
So,
yes,
so for the second expression for GM,
yeah,
is it supposed to be V capital DS by V capital GS? If it's capital GS, then the expression doesn't match.
no,
It
it's
should
not it's not capital GS, it's basically
small GS.
small GS, yeah, small GS. It is at VGSQ, VGSQ. Okay,
Okay,
and then
thanks.
you can replace this with this one. So uh, we can plot IDS versus VGS. Okay, and you will get something of this sort. Here VTH is this. Okay, beyond VTH you will get current, and we can basically have we can vary your VGS. Okay, and you will get variation in IDS that we know. Okay, right. But if you take a slope here, if you take a slope, that's basically your GM, right? That is how we have written. If you take a slope here, you will get GM. Now GM is transconductance, and another important parameter in small signal model, that is R naught. Okay, that is output resistance. Why this is coming? As we know that this IDS VDS curve, this is not flat, and there is a so we can have a resistance which is often known as output resistance. Okay, and this can be, in fact, IDS can be written as Kn VGS minus VTH whole square. Okay, along with there will be another term 1 plus lambda VDS. Okay, this lambda VDS is coming because of this to express this tilt. Okay, this lambda is often known as channel length modulation. Channel length, I don't know what happened to my pen today. Channel length modulation. Okay, so this that is once you are increasing, you remember we increase VDS, the channel moves away from the drain side. So that is basically channel length modulation. So the effective L will change. Okay, so this factor comes because of this tilt, and you can find out R naught by assuming I mean by just taking the derivative of IDS with respect to VDS at constant VGS. Okay, or VGSQ. This of course with inverse, or you have to do del VDS over del IDS. So if you do that, you will end up with you will get VGSQ minus VTH whole square whole inverse. Okay, and you can basically simplify it a little bit more by assuming this IDSQ. Okay, of course that has to be this one. Okay, so this is basically your R naught, that is the output resistance associated with your MOSFET. So we can use this GM and R naught. Mind that there is no R pi because there is no current flowing through the gate. Okay, so there is no equivalent of R pi what we got in BJT, because BJT has base current. There is current through base, but here there is no current through gate, right? Because there is an insulator gate oxide, so there is no current through gate. So when we draw the small signal model, we can simply so say this is my gate, this is my source, so this is your GM VGS, because you see the output characteristics of the MOSFET is effectively a constant current source in the saturation region, and that current source can be written. So if this is your VGS, okay, if this is your VGS between gate and source voltage, the corresponding constant current is GM VGS. Okay, and there is resistance here, that is basically R naught. Okay, right? So this is your drain and this is your source, this is your gate. So this is basically the small signal equivalent circuit. Small signal equivalent circuit. Now equivalent circuit of MOSFET. So now what happens when we apply, when we actually use the MOSFET in a circuit form? Let's just try to draw the circuit which only contains RD. Okay, in that case you see then the small signal model will change a bit, because we have to consider R naught as well as RD. Okay, so this will be your drain, this will be your source, and this will be your gate. This is your VGS and this is your VDS, or you can write V out. Okay, which one is so this is because you remember in when we do when we apply when we talk about a small signal model, although there is RD here and VDD here, and of course there will be a DC voltage here. Okay, but when we talk about small signal model, we need to remove all the DC voltages with ground. Okay, so we will end up with so this RD will be, so this is RD will be effectively, one side will be grounded and the other side is connected to drain, right? Because the RD one side is connected to drain and the other side is connected to your VDD, that is the supply voltage. Okay, now the supply voltage you are shorting to ground. So you are removing supply voltage and putting it to ground. So what will happen, this RD is between drain and ground, so you see R naught is between drain and source, right? So effectively R0 and RD in parallel. So that is what I have drawn here, R0 and RD in parallel. And we will have, this is your small signal equivalent circuit. Now we can find out the corresponding gain, okay, which is pretty easy in this case. You see V out will be equal to V out here, V out will be equal to GM VGS, that's the current, okay, GM VGS multiplied by R0 parallel RD, that is your V out with a negative sign, okay. So V out will be GM VGS, that's the current, okay, but the direction of current and the direction of current is like this, but voltage we are considering plus at the top and minus at the bottom, so we have to take that negative sign, okay. So GM VGS are not parallel RT, right, that is V out, and VGS is basically your V input, because that's I am assuming there is no resistance at the input side, okay. So VGS is basically V input, right. So we can write gain, voltage gain, V out over VGS, that is equal to GM minus GM R0 parallel RT, okay, minus GM R0 parallel RT. Now this is the simplest amplifier circuit as far as the common source amplifier is concerned, because this is common source configuration, because source is in between, because source is if I go back, where is the circuit, okay. So where is that circuit, sorry. So you see the here source is basically, so this is your source is basically grounded, and this is between input and output, this is your output, right. So that way it is a common source configuration, and the gain we have found out is the simplest I mean for gain for the simplest common source circuit as far as the amplifier is concerned. Now we can similarly we can have basic common source configuration with biasing, okay. We will not go through different biasing technique in this particular MOSFET section. We have done that in BJT. We'll just take the voltage divider kind of biasing, you remember. So we will have so this is your biasing resistors. So what we are doing, we are using common CS, common source configuration, okay, as far as the amplifier is concerned, and in this common source configuration we bias the circuit. So this is our VDD, okay, this is R1, this is R2, this is your RD, because this resistance is connected to drain, and source is grounded, okay. And here we have applied a capacitor, because you see we need to isolate this AC signal from the DC signal, right. So what we can do, we can to make it more generalized, we can put a resistor here, that is the resistor of the that is the resistance associated with the AC signal, okay. Let's put a resistor here, RS, okay, and this is your VS or V in, whatever, okay. So that's our basic common source configuration with the biasing resistors, and the capacitor we choose in such a way so that the impedance of the capacitor, okay, impedance of this capacitor is, we can write obviously 2 pi FC, so this is CC, okay, coupling capacitor, and we have to make sure this Z associated with coupling capacitor for the input frequency range such that the input signal barely notice the presence of this capacitor, okay, but it will effectively isolate AC and DC signal, right? Now we can again, so this is our V out, okay. We can carefully draw the input signal model of the BJT. So this is your GM VGS, okay. This is our source, because source is grounded, you see. So source is grounded. We have R0, okay. We have RD, right? And this is your V out, and the corresponding input side. This is your gate, okay. And there is R1 and R2 in parallel, okay. Because you see VDD, you are putting it to ground, right? So in that case, this is the common point, right? This is the common point at the gate, and the other point of R1 is grounded, and other point of R2 is also grounded. So R1 and R2 effectively in parallel. One point to be noted, in case of BJT, we use Thevenin theorem, or we consider that there is IB is much less than that of the current here. That way we were assuming voltage divider formula, but here, as there is no current through gate, so we can directly find out the voltages and all that, DC voltages. Anyway, so these R1 and R2 in parallel, okay. And of course there is RS, because we are assuming RS is there, and there is VS, okay. So this is your and of course this is your VGS, because that is the gate source voltage, right? So this is my small signal equivalent circuit, and we can write V out, okay. V out equal to minus GM VGS, okay, R0 parallel RD. That is V out with a negative sign. And what about here? You see, like in the BJT we discussed, the VS is divided in two parts. One is across RS and the other is R1 parallel R2. But our interest is VGS. So VGS will be basically the voltage dropped across R1 parallel R2, right? Now this, so we can write VGS equal to R1 parallel R2 over RS plus R1 parallel R2, okay, multiplied by VS. So that's basically your VGS. This is pretty straightforward, okay, because we are basically we need this voltage drop VGS, which is voltage drop across R1 and R1 parallel R2, and that can be, you just use this current multiplied by the this resistance. That's basically your VGS, right? So if you do that, so this is your VGS, so you can put that and you will get V out over VS, because that's the gain, okay. V out over VS is basically your gain, and that is minus GM R0 parallel RD, okay, multiplied by R1 parallel R2 and RS plus R1 parallel R2, right? Correct? Because you just put it, it is pretty straightforward. Because you can V out versus VS, you can write V out versus V out versus VGS multiplied by VGS by VS, right? So this and V out versus VGS is known to you, known to us, that is this value, and VGS over VS is this, right? So that way that this is the gain of the circuit, and you can basically you can find out R out. R out is nothing but R naught parallel RD. Okay, R out is R naught parallel RD. Okay, and you can correspondingly also find R in and all that, right? So we can complicate the situation a bit, like we did in case of BJT, by assuming that we have the source is not directly grounded, rather we have a resistance connected between the source and the ground. So if I redraw the circuit, so this is my RD and this is my RS, okay, and again this is my R1 and this is my R2, okay, and this is your VDD, okay, and correspondingly you can use VS or whatever, okay. So and this is grounded. So again you can draw the small signal model, okay. Let's for the time being don't consider RS and R naught, okay, to simplify the situation. Then you will then we will have, this is your VS, but you can again, this is, you can again directly consider also RS, it's up to you, okay, because so this is R1, this resistance will be R1 parallel R2, okay, and that is basically your gate terminal. Now you see this is grounded, but what about here? Here we have GM VGS, okay, and this is my source terminal, and from source there is a resistance RS, and that is basically grounded, okay, and there is a resistance RD which is grounded, and this is your V out, okay, and of course this is the voltage, drain source voltage, gate source voltage VGS, right? So this is the equivalent circuit. You see the source is not grounded, source is through a resistance, it is grounded, okay, that resistance is RS. So that's the difference. Now what we can do, we can again draw the, we can again find out the gain, okay. Gain will be in this case gain will be GM, I mean the V out will be GM VGS into RD, if we haven't considered the effect of R naught, which is minus GM VGS RD. What about VS?
So can you go to the previous slide?
Yeah, so yes, so what about VS? You see VS, yeah, VS has two parts. One is the entire VS is across R1 R2, right? So if you consider another RS, then you have to take into account the effect of RS, and then the voltage across R1 parallel R2 will be less than that of VS, that we have seen before, right? So you see this is your I am just not considering RS for the timing, so entire VS will be across R1 parallel R2. However, this VS has two parts. One is VGS and another is the voltage drop across RS, because you see Vs is between gate and ground. Okay, Vs is between gate and ground, and here you have to so this VGS is between gate and source. Okay, this VGS is between gate and source, and so we have to consider here. So if I show here, so this Vs, okay, it has two part. One is the part here, okay, which is nothing but VGS, okay, and the other part is here, which is voltage drop across RS. That is all I wanted to say. Okay, so if that is the case, then what we can do, we can write Vs is equal to VGS plus GM VGS into RS. You see, because you see here current is GM VGS flowing through RS, so give rise a voltage drop whose polarity is matching with the polarity of VGS. So we basically add them up. Okay, so GM VGS, current is entering, so voltage drop will be obviously polarity will be like this, and so you can we can have like Vs is VGS plus GM VGS RS. Okay, so right, so in this case we can again find out the gain expression. Gain expression will be V out over Vs. Okay, gain expression will be V out over Vs, and so gain you can straight away write voltage gain in this case V out over Vs. Okay, that is with a negative sign GMRD, okay, by 1 plus GMRS. Okay, so so similar like in BJT, here also the because of RS the effect will the gain will decrease. Okay, you remember in case of BJT we use RE, that is the resistance which is associated, which we connected between emitter and ground in case of common emitter amplifier circuit, the degenerate amplifier circuit, and in that case the effect of RE was to reduce the gain. Here also RS, because of RS your gain will be reduced, but if I mean if your if the I mean you can simplify this expression AV equal to minus RD by RS if you consider GM RS is much greater than 1. If you consider that, then you can end up with that expression AV nearly equal to minus RD over RS. Right now, to sum up, just one point I would like to mention. You can what we sometimes do, probably you have seen in your lab experiment, that we can use we can bypass this resistor. Okay, we can bypass this resistor RS to improve the gain. Okay, and sometime what we do, we partially bypass it. Okay, if we need we can partially bypass it, but this bypass capacitor we choose in such a way so that the AC signal will see this as a short. Okay, again 1 by 2 pi f c, this the capacitor impedance will can be capacitor value can be chosen in such a value that the AC signal will see it is short. In that case your gain will remain intact, but this RS will act as a negative feedback and will improve the biasing stability, right? This is we have discussed in BJT also. So this is in a nutshell common source amplifier circuit. We will not discuss common drain or common base MOSFET amplifiers. Okay, we will not discuss that. That will be covered in analog electronics class. Okay, so we will restrict ourselves only in the discussion of common source amplifier. Okay, here to summarize, we have so far discussed the small signal model, and we have particularly considered two cases. One case is where there is no RS, and in the other case there is RS, and the effect of RS will reduce the gain, but it will improve the stability of the biasing. But you can improve the gain if you bypass this by using a capacitor. So RS will be there for DC signal, but for AC signal RS will be shorted through this capacitor. Now you have to apply a output capacitor also, because often we use a load to take this. Often we use a load. That load may be the next stage, input impedance of the next stage possible. Okay, so that this resistance or this impedance doesn't change the biasing of this amplifier. Okay, so you remember in case of BJT also we use a capacitor at the output signal, and also if we don't use this capacitor, we will have DC and AC both here. Okay, and this DC and AC both can affect the biasing of the next stage. So if I have a next stage here which has its own next stage here, okay, which has its own biasing, and we will be only interested in that case only the AC signal, right? Maybe we want to amplify, or we want to amplify, or we want to attenuate, or whatever. Okay, we want to process this amplified signal, and then the signal we will use is basically we should use the amplified AC signal, not the DC signal coming from here, because then that DC signal will change the biasing condition of this next stage. Okay, so this is same in case of BJT amplifier also. So we use a capacitor here, we use a capacitor, bypass capacitor to bypass RS, and we use a capacitor at the input so that is biasing of this part remains intact. Okay, so this is in a nutshell the small signal model of the MOSFET as the common source amplifier and common source amplifier. Okay, so next day, that is tomorrow, we will start another chapter which is known as op-amp. Okay, so tomorrow we will start another discussion which is op-amp. So if you have let me go back.